There we go. So we should be streaming now. So let me see if there are any questions prior to starting the class. Alrighty. Okay. Excellent. And as you can see, this particular module has not been updated since last summer, because I was teaching a summer class, and that was the last time this module was actually updated. I think it was a minor thing about the notation. And then starting fall, I'm going to go back to teach on campus. So that should be exciting. After the STEM building has been done for almost 2 years, finally, I can start to use my office and also the brand spanking new classrooms. I guess so. So CS is kind of interesting, because CIS, which is referring to the entire department, consists of application classes, core classes where they teach operating systems, how to use an operating system, and then we have networking classes, security classes, and the web classes, and then finally we have the programming classes. So all of the other disciplines, anything other than programming, they have been teaching online for a long time. It's the CISP classes that were kind of the last one to move online because of the pandemic. Partially because of I think it's partially because of the complexity of the topic. It is harder to teach online, effectively. So I think there will be continuing to be hybrid format, because some teachers like to do the inverted classroom, where the face-to-face portion is actually the lab or the assignment portion, and then the lecture portion is online. So it depends on each professor. I'm just gonna go 100% back on campus. So it's going to be all face-to-face. All right, it is time to start, and I am going to get started here. I'm just looking at the time. It's 31, so it really is time to get started. So I got some kind of points here prepared here, just so that we can get started. All right, so the first topic is to talk about what is a base 10 scientific notation. So we talked about this, or I didn't talk about it, the lab did on last Thursday. So 12E34, if you type this in C or C++ in a program without quotes around, obviously, this is interpreted as 12 times 10 to the power of 34. So I just want to make the terms clear in this case. The 12 part. Oh, right, I'm not screen sharing. Thank you. Forgot about that. Thank you, thank you. There we go. There. I forgot about that. Sorry about that. So anyway, this is the kind of the outline or the plan that I have kind of written, so that I can remind myself what I need to talk about. All right, so starting from the beginning. So when we look at 12, 12E34, it is actually just representing the value of 12 times 10 to the power of 34. And this is all in base 10. Okay, this is all in base 10 because I want to make sure that people are comfortable with the base 10 scientific notation before we move on to binary. So the 12 part here is the Mantissa, and you can see that I have put Mantissa into double quotes, because that's actually not how Mantissa is defined. There are several, I wouldn't say conflicting, but there are several alternatives to define what is Mantissa. But in this class, okay, in this context, in the context of this class, we're going to use this particular definition. So technically speaking, if you ask a mathematician, the mantissa M should be normalized so that it is always greater than or equal to 0 and then less than B, where B is the base that we are using. So if you're using base 10 like in this case, then B is supposed to be 10. The proper term of the 12, in this case, if you ask a mathematician or a math professor, what is the term of this 12 here, 12 times 10 to the power of 34? Your professor is likely to say, well, there are no actual specific term for it. You can call it the multiplier of an integral power of 10, which is very descriptive, right? But it's really long, okay? And that's why I don't want to refer to it as the multiplier of an integral power of 10. And then later on it's going to be the integral power of 2, but nonetheless, we're just looking at a coefficient or a multiplier. So in this class, the way I define mantissa is simply, so I use the term mantissa to refer to the coefficient or the multiplier of an integral power of a particular base, and we're dealing with base 10 for now. And then I'm going to use the specific term of normalized mantissa when the mantissa is meeting this requirement here, that it is greater than or equal to 0 but less than the base. So are we okay in this case with all the terms? Because that's the first thing we need to do, is to make sure all the terms are clarified, because then we're going to be referring to these terms later on. Okay, we got some questions. Okay, so we got yes, which is good. And if anyone has any questions at this point, you'll just kind of let me know, because unless we get all the terms clarified, it's really hard to move on. All right, excellent. All right, so the 34 part, okay, like in this case, the 34 part is really the integral. In this case, integral has nothing to do with calculus. It is simply meaning that it is an integer value that serves as the exponent of 10. All right, so 12E34 is also 1.2 E35, because in order to represent the same value, when you divide the mantissa by 10, then you have to make up for the division by 10 by changing the exponent of 10 and bump it up by 1. So this way we preserve the value that we want to represent. So I think that's pretty much all I want to make sure that everybody understand at this point. So this is really just the beginning of today's lecture. It's kind of a little bit of a recap of what your lab was about from last week. So I'm not seeing any questions, and I think most people are on Discord. Yeah, so there are about, I'm just going to kind of guesstimate, about 20 people on Discord, which means, because this class still has 50 plus students, so I should be seeing about the same number of people on YouTube. And let me take a look. Yeah, so it's about the same on YouTube, so that's kind of what I would expect. And all right, so it's all good. I'm going to close my browser on YouTube because there's no need to have it stay open. All right, so what we'll do now is to kind of get into the discussion, formally, and we are going to get into section 2. So section 2 talks about the IEEE floating point number representation, which you normally know as float in C++ or double, depending on the size of the floating point number representation. Float, which is the shorter one, it uses only 32 bits. It's not really used a whole lot anymore because it lacks precision. And modern processors, like just pick any processor off the shelf on a laptop computer, they are more than capable of dealing with 64-bit floating point representation. So most of the time we kind of default to the double precision floating point number, which is 64-bit wide, as opposed to the single precision floating point number, which is only 32-bit wide. And this is a hyperlink for a reason, because I think Wikipedia has a very good graphical representation, and I don't really think that I need to replicate it. So we're going to kind of fast forward to the Wikipedia representation. All right, so now we have 64 bits. Okay, we have bit 0 all the way on this side because we put all the least significant digits on the right hand side and then the most significant digit on the left hand side. But in this case, you have to be careful because this by itself is not a 64-bit number per se, because it's really just three sections. Okay, there are three individual components that makes up the 64 bits. Bit 63, which is the most significant bit, is called the sign bit. Now, I understand we talk about the signed integer representation, but in this case, the sign bit is really quite simple. All it does is to say if the sign bit is a 1, then the value being represented is negative. If the sign bit is a 0, then the quantity being represented is non-negative. That's all it does. Okay, it doesn't really say, oh, let's multiply 2 to the power of something and subtract it from the sum, which is what we did with signed integer representation. But in a double representation or single representation or any type of floating point number representation, the sign is really just an on-off switch. Okay, is it non-negative or is it negative? That's all it does. The exponent is not really a very good description. Okay, I'll talk about this in just a little bit, but at this point I'm just going to say the term exponent, that is from bit 52 to bit 62, so there are 11 bits, for this exponent. It really should be called the biased exponent. Okay, so for people who are taking notes, okay, I think you're already kind of jotting it down and go like, okay, this exponent is actually biased. And if for people who are not taking notes, okay, now might be a good time to start taking notes. Because the concept of biasing the exponent is going to be important. Okay, it's not difficult to understand, but it really is a part of the specification that deserves some attention. And then the rest of it is only called fraction, but it really is not a fraction. It is the fractional part of the mantissa. Okay, so all of these terms are kind of awkward, right? The exponent is biased, and then this is not really a fraction. It is a fraction of the mantissa, okay, which is basically everything after the point. So this is where the verbal description of how a double precision floating point number is formatted is clumsy. Okay, and that's why we got mathematical notations. So we have two mathematical notations here. One is this one, the first one, and the other one is the second one. I personally prefer the second one because the second one actually does use some of the notations that we have been using, even though it's using B, for what we usually call D. That's basically the same thing. All right, so let's go ahead and take a look at what we are talking about here. I just want to see whether I want to replicate this so that I can refer to it in my notes or not. Let me right click on it. Nope, this does not give me the I probably need to install an extension so that Wikipedia can give me the LaTeX format, but I don't really need it. I can just type it myself. All right, so let me just go ahead and kind of talk about this, a double, okay, and I'm going to use the formatted double here because we're referring to the type double. Has 64 bits, okay, 64 bits, and we're going to call these things from D for digit 0 to D underscore 63. So there are 64 digits, and they range from, oh, I'm missing a D here. There we go. So in terms of notation, we are just looking at the digits as D0, which is our least significant bit, to D64, which is quote-unquote the most significant bit. But I have to emphasize that there are three components inside these 64 bits. So this is really just a way to designate which bit are we talking about. And if there are any questions about the notation, at any point, just go ahead and ping me in the text channel, because nothing is worse than not understanding the notation itself, because that's the language. Okay, we are expressing something, using the mathematical language. So if the language itself is not clear, then it becomes kind of difficult to understand, what the concept is and how to get things done. All right, so I'm going to put in my own equation here. So just be a little bit patient when I type it out. So the first part is -1 as a value, and this is raised to the power of simply d underscore 63. So I'm just gonna put this into, yeah, I forgot about the curly braces. There we go. All right, so let's take a look at this, just this portion here. Okay, this portion is basically saying, we look at one single bit, which is bit 63, the most significant bit, and then we raise -1 to that power. Well, since D63 is just a single bit, right? It's either 0 or 1. -1 raised to the power of 0 is 1, because anything raised to the power of 0 is 1. But -1 raised to the power of 1 is -1 itself. So this is one kind of tricky way, kind of mathematician sort of way to determine, are we multiplying the rest with -1, or are we multiplying the rest with just 1? So if you don't like this format, okay, you can always use a ternary expression and say, if D63 is a 1, then use the value of -1. Otherwise, use the value of 1 and then put parentheses around that ternary expression. It would mean exactly the same thing. Are we still doing okay so far? Any questions? We're all good? Okay, so far so good. I got some confirmation, which is good. But I really cannot tell whether the rest of the class. So D63 is, yes, it's kind of the sign bit, yes. But it doesn't work the same way as the sign bit in a signed integer. So you just have to be super careful with that. All right. All right, so next component. Okay, let's take a look at the next component. For the next component, we're going to look at the mantissa. Okay, so the mantissa is a little bit strange. Okay, the first part doesn't seem too strange. Okay, we have a sigma, a summation, where I goes from, I need to think about this a little bit. It goes up to bit 51. Okay, so I goes from 51 to down to 0. Okay, so we can do that. And then okay, I'm going to close it first, just so that you guys can see the actual sigma notation. And then what we are summing, what we are adding together, would be d subscript of I. Okay, that's the easy part, right? Because I is really designating a specific bit within the 64-bit representation. The tricky part is what we are multiplying it with, because normally we multiply d subscript I to 2 to the power of I. Not in this case. Okay, so in this case, the most significant bit, which is bit 51, is actually multiplied to 2 to the power of -1. So that means when we specify which power of 2 we're multiplying it to, now we have to specify a little bit more carefully. So that's going to be I minus 52. So that when I is 51, I minus 52 is going to be -1. All right. So I'm going to pause a little bit here just to make sure that you guys are understanding that this is not your typical way of looking at the bits. Okay, everything is, you can just look at this as everything is shifted. Okay, that's one way to look at it. So let me just kind of pause and see if there are any questions about the sigma notation. In fact, I am going to, for now, I'm going to break it up into 2 separate bullet items. So this way you guys can just refer to, you can separate this specific item from the previous one, even though it really is one of the components, but I'm going to break it up. Why does the sigma go from 51 to 0? Well, that's because that's the way the IEEE notation works. I did not decide this. this decides it. The IEEE, decides it. Because, I is really just designating which bit are we looking at. Or is below, just asking about the fact that how come we are decrementing and not incrementing. I didn't. Okay. All right. Fine. So if you guys don't like, decrementing and prefer to be incrementing, we can just change that, right? I mean, we can just change it from 0 to 51. Okay, that's pretty easy. 0 to 51. There we go. It doesn't change a single thing. It just changes, which way we are moving I. Are we moving it from 51 down to 0, or are we moving it from 0 up to 51? Nah, it's okay. It's all good. Any other questions about this part? Yeah, so Tam is correct. That's because I am looking at it from left to right. But that's kind of either way it's fine. Okay, it really is just a matter of which way do you prefer I to move. So it's not a big deal. But this is the part where it goes like a little strange, because I'm gonna say there's a 1 plus here. There's an extra 1 that has nothing, absolutely nothing, to do with any bit within the 64 bits of a double. That 1 is just going to be here all the time. All right. And then Tam is typing something. I'm going to wait a little bit. It's not going to be that bad. I'll give you guys some examples. We can figure things out pretty easily here. All right, so now the third component is a component where we are specifying an integral power of the base. Now, since we're dealing with bits, right, bit, so a bit is really a binary digit. That's why we spell it as bit. So as a result, our base is 2. So now we have to specify, all right, so what kind of exponent do we specify and say that this is, the multiplier is multiplying to 2 to the power of blah, right? Okay, so here's 2 to the power of. So this is the part where it gets a little bit interesting, because it's going to be another sigma notation. So now we have another summation. And the summation is going to start from bit 52 to bit 62. So there are 11 bits to specify here. And obviously we have to designate which bit we are talking about. So D subscript I. Oh, I forgot about I equals 2. So this is I equals 2. Okay, there we go. Yeah, I know this is a little bit hard to read now, because we have a sigma notation as to specify the exponent of 2. Now the question is, what are we multiplying d of I to? So obviously it's still going to be 2 to the power of something. So this is going to be 2 raised to the power of, yes, this is going to look a little bit awkward. So what we want is we want bit 52 to be 0 here. So it's going to be I minus 52. I minus 52. There we go. So we have, and this is not, I'm not done yet, okay? Because if this is how we specify 2 to what power of 2 we want to raise, we want to specify, then we cannot represent very small values, right? Because we can no longer specify a negative power of 2. We can only specify non-negative powers of 2 if this was the actual equation. So somebody, okay, hopefully someone in this class is already thinking, oh, we can use the signed number representation. All we have to do is to say, oh, we look at the most significant bit of just the exponent portion, and then we subtract, 2 to the power of whatever power of 2 is that's corresponding to that digit from the summation of the rest, okay? Because that's what we did with signed integer representation. And if anyone is thinking, I have no idea what you're talking about, well, there's still time to study before Thursday. Okay, I'm just going to say it that way. Well, okay, that would be the way a computer science person or a mathematician is going to think about this. Engineers are not mathematicians. They're very, very good at math, but they are not mathematicians. So instead of doing that, instead of using the signed representation, they decide that they want to specify. Okay, I have to find out which way to close it. There we go. So they decide that they want to do something like this. This is where the bias is coming in. Oh, actually, I put the minus 1023 at the wrong place. Okay, it actually belongs here. There we go. So the 1023 is in base 10. Okay, and this is why it's called biased. Okay, we basically use a 11-bit pattern to specify a non-negative integer, and then we subtract 1023 from that specific integer, which is actually unsigned. It's going to be a natural number. But after the subtraction, we can potentially end up with a negative integer, and this is how we get to the negative powers of 2. So, with these three components, what are we going to do with the value? What is the value being represented by a double, right? I mean, that's going to be the big question. And I'm just gonna keep an eye on the text channel because Tim is typing. All right, so I'm just gonna say t. Oops, sorry, not t. V of value and then I'm gonna use subscript d for the value represented when we look at the bits as a double. Oh, that's not gonna work because that's gonna be another d over here. Okay. I'm just looking at this. Maybe just change this one to F. Floating point. There we go. Alright, so that's going to be this number. And then I'm merging the lines now. Okay, I'm concatenating the lines that we have. And then concatenate one more time. This is the value represented by a 64-bit pattern that we call D when we choose to locate it as a double precision floating point number. Okay, so Tam typed in the text channel, wait, does that mean if a signed 3-digit double is negated as... I don't think so. There's no negation happening. Oh, subtracting a power of 2 minus 1 does not help with negation. So there's no ones complement or bitwise not involved in any part of this math here. All right, so this is the bottom line. I mean, if I have to summarize, if I were lazy and I just go like, if I want to teach double precision floating point number to a class, I just have to leave it as this, and I'm done. I'm done and ready to move on to the next topic. Obviously, this is a little bit hard to interpret, right? So what we're going to do is we're going to do some experiment. Okay, we're going to say, I have this specific v f of d that I want to represent. I want to use this equation here to figure out all the individual parts. So that's what we're going to do next. Okay, so we are just going to utilize this notation here, and then we're going to reverse engineer and find out, okay, if I want to represent a specific value, how is that going to look like in, what zeros and ones do we use to specify all 64 bits of a double precision floating point number. So before I move on to actually do that, I want to make sure that everybody understand what I am about to do. And Bilal has a question or a point, so I'm going to wait for that too. But for the rest of you, just kind of think about it, okay? Do you understand what I am about to do? All right, so Bilal said, when you earlier said, all I'm going to say is, there's still time left to study. Signed representation, signed integer representation. That's what I was referring to. because the most in a signed integer representation, the most significant bit is multiplied to the corresponding power of 2, but it's not added to the sum. It is subtracted from the sum of the rest of the bits. Exactly. So Chris is right about that. All right. Shall we get started with this? Yep, it is ms lowercase b. So I'm going to type that here. Because uppercase b is typically used to represent a byte, and then lowercase b is used to represent a bit. So it is case sensitive in this context. All right. So any other questions before we actually move on and do this one experiment? All right, Eric is typing. Very good. All right, so I'm gonna wait for Eric, but I will, kind of give myself a specific value to represent here. So let's go with, oh, I don't know, 25, negative 25 point. I'm just trying to think of, what would be good value. 625. Okay, so this is going to be the value that we want to represent using a 64-bit double precision floating point number. But I want to emphasize that this is actually in base 10. Alright, so Eric is typing in regard to the sum. When we changed from decrementing to incrementing, shouldn't we have changed the exponent? Nope. Nope, we do not need to change it because all we are doing is to change how we got from one end to the other end, but we are not really changing the range of values that I has to go through. It's still going to be the same range, which is from 0 to 51. So it really boils down to a matter of, do you want to count up from 0 to 51, or do you want to count down from 51 down to 0? But it makes no difference in terms of the value or the expression that we are summing over this sigma notation. Yep. All right. So let's get started with this, right? The first thing we need to do here is base conversion, and also recognize what sign we are dealing with here. So the sign is easy, right? So right here we can just say d underscore 63 equals to 1 because the value is negative. Are we good so far? That's really simple, right? Because the value is negative. And I'm going to add some more notation here just so that I can refer to those things a little bit more easily. And now I can use a mathematical notation because v is less than 0. Is that okay? Because this way is a lot more precise compared to what I did earlier, because now v is very specific. We are trying to represent a value of negative 25.625 in base 10. So now the sign is taken care of. The rest is now to try to figure out this portion here. Okay, that looks pretty darn nasty, right? So we're not gonna be intimidated by how nasty this is gonna look. So we will proceed to do the normal base conversion after we just take the absolute value of v. So now we look at 25.625 in base 10. And then we ask, how do we represent this value in base 2? All right. So this is, convert to base 2. Okay. Do we know how to do this? If the answer is no, then I would also suggest those people to study a little bit more, because even though double precision floating point number is not in the scope of the exam on Thursday, base conversion is. And this is all about base conversion. Okay, I'm not asking anyone to do actual conversion into a double. I just want to convert a specific value, 25.625 in base 10, into a binary representation. That's all I want to do at this point. So base conversion is about specifying a specific value using quantities of integral powers of whatever base we choose to use. So it helps to understand what are the powers of 2 that might be handy in this case. Tam is fast, so I'm just going to list here all the powers of 2 that we might find handy here. Okay, I start with one that is not handy, that is useless, but but that's not bad, because this way it is obvious why we have something that is useful and something that is not useful. So 0.5 is just 1/2, 0.25 is 1/4, 0.125 is 1/8, and those are all integral powers of 2, because an integer can be negative. So 0.5 is 2 to the power of -1, 0.25 is 2 to the power of -2, and then 0.125 is 2 to the power of -3. So these are all powers of 2. Okay, and when I don't use a little subscript thing or put a number in parentheses right after the number, these are all in base 10. So now I'm going to specify just remember the change example, right? When your currency can only have values of 1/8 of a dollar, 1/4 of a dollar, 1/2 of a dollar, 1, 2, 4, 8, 16, and $32. How do you make change for $25.625? $25.625. Okay, it became that specific question. So with this, we can just go like, oh, okay, it's 16 plus 8 plus 1. That takes care of the 25. And then the 0.5 takes care of the 0.5 out of the 0.625. And then we have only 0.125 left. We don't have a quarter. All right. I mean, that should be easy, okay? Because by now, we should be pretty used to doing quote unquote base conversion like this. Base 2 is specifically easy because all it takes is a compare to see if there's a presence or an absence of a power of 2. There's no actual division. Now, if I ask you to convert this into base 4, for instance, okay, then it gets a little bit nastier because now you actually have to do division. But base 2 does not involve division. Base 2 only involves comparison. If it's greater than or equal to, you have that specific power of 2. If not, then you don't have that specific power of 2. So base conversion in base 2 is particularly easy compared to other bases. But then you can always apply the formula that I have introduced in the notes, right? It just takes a little bit more work because you have to kind of punch it in. If there's a division, there's a power to, then you have to do the floor, and then you have to do the mod. It will still work. It's just that in this case, it can be a whole lot easier, doing it the other way. Sure. If you want to, you can do a conversion in base 4. Yeah. But I'm gonna move on with this in just base 2. So 16 is 2 to the power of 4, right? So now I'm going to use mathematical notation because the 16 is 1 followed by 4 zeros in base 2. So I have to emphasize this is now in base 2. The 8 is 1 followed by 3 zeros in base 2. The 1 is 1 followed by nothing in base 2, so it's going to be just 1 in base 2. 1 is 1 in whatever base you're in, so it doesn't really matter. The 0.5 is 0.1, 0.1 in base 2. And then the 0.125 is 0.001 in base 2. So now we have all the components of the base 2 representation, and all it takes now is to kind of just add these up. So, and you might say, but when we're adding binary numbers, shouldn't we worry about carries? Not in this case, okay? Not in this case, because we can only have up to 1 1 for each bit position. So there's no way we can end up with a carry. So all we have to do is just to find out, okay, there's one at the bit 4, 1 1 for bit 3, no nothing for bit 2, nothing for bit 1, 1 1 for bit 0, 1 1 for bit negative position 1, negative 1, and none for negative 2, and 1 for negative 3. And now we have our base 2 representation. And Tam was right. I'm pretty sure Tam was right, like when he posted, when he or she posted 110001.101. But this way we know how it is derived. Cool. All right. Excellent. Now what do we do, right? This is, by the way, this is old stuff, okay? You can consider this a review of the material that might be, on your exam on Thursday, okay? This is like old stuff, okay? Not new stuff. So the new stuff is look at this and go like, well, we can always look at this and say, I like to look at this, as a mantissa. And I'd like to look at this, and say this is multiplied with 2 to the power of 0. Would anyone complain about this? Okay, not about that it looks kind of redundant. That well, why do we need to do this? But in the sense that you disagree because now we have changed the value that we're trying to represent. And if I want to be very specific, we can now say v is this, and then v is this, and now we say v is this. In other words, we're preserving the value of v the entire time. We are just trying to figure out how to represent the value v. Are we still good? All right. And we got a few people typing. I might. In my in-person class, I actually would have a computer right in front of me, so I could just program a few buttons on the screen, and I can probably look at some of the Olympic Games stuff and just kind of take a sound clip out of it. All right. So now what do we do? Now we look at this and go like, attack this mantissa here. It's not normalized, okay? Because a normalized mantissa, should be greater than or equal to 0, but less than whatever the base is, right? So, okay, it's not in the format that we want. It is kind of what we want. There we go. All right. So what we're going to do here is, I'm not sure whether this will work or not. This is supposed to be a line feed. And it does work. Okay, I am impressed. So now the question is, can I align the equal symbol? And this may not work. Yeah, it doesn't look like that's going to work. Nope, that doesn't work. Darn it. All right. So what we'll do is we're gonna we'll chop the line this way and put it. No, it doesn't like that either. Oh, this is. Oh, that's because I have a space at the end. That's why. Okay, so now we can break it up into several lines because this is going to take some it's going to take a few lines to represent. All right, so that's good. I figured this part out. All right, so now we're going to look at this and go like, well, how about we shift the point to the left-hand side by just one position, okay? So now we have 1, 1, 0, 0 point, 1, 1, 0, 1 in base 2, c dot, times 2 to the power of what? Okay. I'm going to put it this way so that it's easier for you guys to see. What should the question mark be? All I have done is I am moving the decimal point or the binary point, right? It's not decimal anymore, to the left by 1. So what should I do with the exponent? There's a 50-50 chance that you might guess this correctly. Well, the correct answer is 1. Okay, the question mark is supposed to be 1. Because when we shift the binary point to the left, we are effectively dividing the mantissa by 2. Just like when you move the decimal point in the base 10 number to the left by 1 position, you're dividing that value, the number, by 10. So in this case, because this is in base 2, we are dividing it by 2. But I want to preserve the same value. Look at all these equal signs here. I want everything to be the same. So if one side is divided by 2, I better, somehow make up for that. This used to be 2 to the power of 0. Now it's 2 to the power of 1 because 1 times 2 is 2. So we are incrementing. Yes. Okay, very good. All right. So are we good with this math here? All right, very good. So I'm going to do something that is really boring at this point because I'm just going to say, oh, okay, but this whole thing, if I do this again, right, then it becomes 110.01101 in base 2 times 2 to the power of something. Okay, I'm pretty sure at this point, you guys are getting it. It's like, Tech, do not make us do this. This is really, really boring. Yep, there you go. Okay, so we just kind of increment the power of 2. So I'm not going to bore you with 2 more iterations of this, right? Because I could have done that, but I'm not going to do it. So now we're going to have the final representation, which is 1.110.01101 in base 2 times 2 to the power of something. What would that question mark be? There you go. 2 more times, right? Every time you move that point to the left, you have to increase the power of 2 by 1. So, so that's why we end up with a 4 over here. All right, so I'm just gonna pause and make sure that this math here is okay. Okay, this kind of, oh, I must have introduced one additional digit somewhere. No, I did not. But how come things are not lined up? Oh, I got one extra one. Sorry, that's my bad. Operator error. There we go. Yep, there we go. Okay, so that was my bad. But the idea is just that, right? So now we have a proper normalized mantissa because 1 point blah 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 blah, okay, in base 2 is going to be less than 2 because 2 in base 2 is 1 0, okay? So 1 point blah 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 has to be less than 2. But this is also greater than or equal to 0. So now we have met the criterion because it's singular of the normalized mantissa. Are we okay so far? Does everybody understand why we now have a normalized mantissa? It's in base 2, but it's still a mantissa. And then we have an exponent of 4. So are we good so far? Okay. So Taylor is giving me a PS thumbs up. Okay. All right. Cool. So now we look at this representation and then we go back to this mess here and go like, all right, let's try to figure out the bits. This is nasty. It's not going to be as nasty as you think, actually. Okay. I actually made a poo-poo here because this part here is supposed to be in parentheses, so the 1 plus sigma thing is supposed to be in parentheses. Let me fix that first, and then we'll go ahead and try to figure out the values. So I do apologize that I forgot to put in parentheses because of the order of operation, and So this pair of parentheses is actually necessary because otherwise, this one is only multiplied to the sign, and then the rest is kind of on its own, which is not the intention. So I just wanted to make that correction first. All right, so now we look at this mess. Oh, sorry, this mess here, and then we look at this kind of somewhat clean representation, and then we go like, okay, so which bit has to go where, and how do we figure out this stuff over here? Well, first thing first, right? We got the mantissa. The mantissa is 1.1001101. Ah, we got this one here. This one is this one over here. And it's always going to be there, okay? This one is always going to be there, and I know somebody's already complaining, but how do we represent 0? We'll talk about that later. But then we have to look at this portion here, this sigma notation, go like, oh, that's going to be like 52 bits that we have to specify. What are we going to do with those 52 bits? Well, the first thing is, we need to figure out which one is representing this one over here, the one that is highlighted. That is 2 to the power of -1, right? So if it's 2 to the power of -1, we just have to ask the question, how can I minus 52 become -1? Well, it's algebra, so we want 51 equals to I minus 52. So if you move things around just a little bit, you will figure out that I equals to 51, because 51 minus 52 is -1. Does that make sense? We want I minus 52 to be -1, and to make that happen, we need I to be 51. Are we good so far? All right. So that means this one here is actually bit 51, and the rest is pretty easy, right? The next one is bit 50. This is bit 49, 48, 47, 46, 45. What about the rest? Well, the rest are all zeros. Okay, so that means we have a bunch of zeros as the least significant digits, and we just have a few that are non-zeros, and those are going from bit 51 down for, let's see, 1, 2, 3, 4, 5, 6, 7. So there are 7 bits that we actually have to specify. The rest, we don't care. They're all zeros. All right, so that that helped us figure out a few things, right? Oh, wrong place. All right, so I'm just gonna write a note here, and I'm just gonna do this for a few bits. So bit 51 is a 1. The 50, bit 50 is going to be a 0. And I'll do one more. Let's see, how many do I want to do? Okay, I can actually pretty quickly. Okay, let me just do this, because the first time we do this, I want to be more complete, even though it is kind of a chore. So we got 48, 47. It'd be kind of funny if I can just write code fast enough that I can actually just generate all of this stuff here instead of having to handwrite all this stuff here. But I'm not that fast of a programmer. All right, so below, this one here is supposed to be corresponding to 2 to the power of -1, right? So I need to figure out what I value will specify 2 to the power of -2, so that I can determine where this one it belongs in the 64-bit format. That's basically what I was trying to solve for. All right, so getting back to this, we got 1, 0, 1, 1, and then a 0, and then another 1. All right, does that look okay? 1, nope, I got it wrong. So we got 2 zeros, and then we got 2 1s, and then another 0, and then another 1. There we go. Okay, now it looks good. All right, so I'm just gonna pause here, and see if Bilal is okay with the explanation, and to see if anyone else have any questions about how I designate the values of bit 44 to bit 51. Yes, that is correct. I set -1 to be I minus 52, solve for I, and I has to be 51. That's it. D48. Let's see. D48 is. Oh man, I shifted again. Yep, that's a 1, that's a 1, that's a 0, that's a 1 again. The rest are all zeros. Sorry about that. Okay, let me just double check. We got 1, 0, 0, 1, 1, 0, 1, and then the rest are all zeros. Okay, there we go. But thank you, Justin. You're correct. All right, so now what about the rest of the bits? Tack, you promised us, 52 bits. Okay, you just gave us what 1, 2, 3, 4. I just gave you 8 bits. Well, the rest are all zeros. Okay, so I'm just gonna say d of j is a 0 for j is greater than or equal to 0, and it's up to it's up to 44. Okay, so inclusively. There we go. Are we good so far? I mean, does everybody understand why the rest of the bits are all zeros? And this is just my way of writing like 45 zeros. So instead of spelling out 45 zeros, I just say, oh, the rest of the bits, from bit position 0 all the way to bit position 44, they're all going to be zeros. Bit 44 is a 0. If we figure that part out here, I'm just kind of including it here as well because it belongs to one of the digits that we don't have to figure out. Exactly. I mean, computer science programming is all about working smarter and not harder, because we are automating stuff, right? We are creating programs so that anything where the pattern is already figured out, we can just go like, oh, okay. Once we figure out the pattern, we just kind of program a computer to do that to repeat that pattern. All right, so we still got. Oh, I do that all the time too. But the thing is, even though it costs you have a net loss of 25 minutes this time, who knows how many times you're going to have to redo that task in the future, right? That's the whole thing about writing scripts. And besides, it's fun. Okay, if writing programs is not fun, I really hate to say it in a really kind of mean way, you're probably in the wrong type of program. I really mean that. Even though it sounds mean, I do not mean to be mean. I just kind of want to remind people, this is not the kind of stuff that you want to do if it is not interesting to you. Well, that's how we figure this out, Bilal. We figure out where this 1 is in terms of the bit position. The rest are just kind of right next to it. I just need to find out where the starting point is. Alrighty, cool. And I'm gonna wait for Cole. Alright. Alright, so So what have we gotten so far? We got the sign bit done. Okay, that was the easy one, because if the value that we want to represent is negative, is less than 0, we are gonna have a sign bit of 1. That's easy. This portion here, we just figure out your bit 0 to bit 51. All right. What about this mess over here? All this is saying is we have to figure out. Okay, so all this part here is to say, we have to figure out somehow this chunk here has to specify a value of, let's see, 4 right here. Okay, so we need an exponent of 4, and this is specifying the exponent of 2, the integral exponent of 2. So now we just have to look at this kind of somewhat nasty portion and say, how do we make this 4? So let me just kind of set up the equation first, and then we'll try to figure out the rest. Okay, so we're now gonna say, okay, we want 4 to be equaling to this stuff here. Let me point out which stuff we are talking about. This stuff over here. So I am not going to retype that, because I can just kind of go back and copy and paste it. If I can copy and paste, why would I want to retype it? Alright, so it's this portion. So we say yank to the end of the line, and then here paste. There we go. Almost there. Just need a little adjustment there. Now it looks almost there, because 4 is really just the exponent, so we don't need to say 2 to the power of anymore. So now we have the equation to kind of figure out. Alright, so you look at this, right, and go like, okay, how do we solve for all those bits? Okay, the first thing is, let's combine all the constants. Okay, let's not look at 4 on one side and then negative 1023 on the other side. I mean, you guys all know algebra. So the next thing we do is to say, how about we just add 1023 to both sides, and so that cancels out the minus 1023 on the right hand side. Are we good? I just want to check. Okay, so we're good. Good. Okay, excellent. Alright, so now we look at this and go like, well, 4 plus 1023, once again, if it doesn't have a subscript, it doesn't have a number in parentheses right after, it's in base 10. Okay, so we can figure this out. Sure, that's 1027. We look at this and go like, oh, so we are still trying to figure out, how many powers of 2 do we have here, except things are just shifted a little bit. Okay, that's all it is. Okay, they're just kind of shifted a little bit. All right. Before we do that, let's go ahead and convert the left-hand side first. Okay, so the left-hand side is 1024 plus 2 plus 1. So now we have powers of 2's over here, and then we want to figure out what is 10 to the what is 1024. This turns out to be 2 to the power of 10, and this turns out to be 2 to the power of 1, and this turns out to be 2 to the power of 0. So now we look at this and go like, I think we know where we're gonna get this done, right? How we're gonna get this done? Because all of the other powers of 2, like 2, 3, 4, all the way up to 9, those are just zeros, okay? Because we don't need any of those powers of 2 in order to add up to 1027. So now we look on the right hand side and we ask, we need this 2 to the power of 10, and what I is going to give me 10. Okay, so we basically say 10 equals to I minus 52, and that means I is what? 62. So bit 62 is going to have 1, and then we just kind of figure out the rest by working out the math here. So in the end, what we end up with is, we'll start with D62, okay, right? D62 is, I need to put braces around it. It's going to be a 1. That is because 2 to the power of 10 is needed. Okay, so I am going to do some copy and pasting here. There we go. The next one is 0. We don't need any 2 to the power of 9. And the rest, I mean, yes, this one is going to get a little boring. The 60 is 0. 59 is going to be a 0. And 58 is going to be a 0. Okay, so let's figure out which one is not going to be a 0, right? Because, otherwise we're going to be doing this all day long until the cows come home, as they say. So we want to basically stop all the zeros when we get to 2 to the power of 1. So now the question is, what is I going to be when I minus 52 is 1? Let's see. Maybe 53, right? So by the time we get to 53, we need to shift back into ones. Otherwise, the rest are all zeros. Okay, so let's go ahead and do that. 57, 56, 55, 54. Finally we got to 53. This is going to be a 1. And then 52 is going to be a 1 too, and that's it. Okay, I just pasted one time too many. Cool. And you guys look at this and go like, and now what? And then I go like, now we got all the bits. We got bit 0 all the way up to bit 63. Don't we? Let's double check. Let's double check. We know bit 0 to bit 44 are all going to be zeros. Bit 45 is a 1, bit 46 is a 0, bit 47 is a 1, bit 48 is a 1, bit 49 is a 0, bit 50 is going to be a 0, bit 51 is going to be a 1, bit 52 is going to be a 1, blah 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 blah, up to bit 62 is going to be a 1, and then all the way up to the beginning, right? Up to the beginning where we have bit 63 is a 1 because it's the number, the value that we want to represent is negative. So we get to bit 63 is a 1. We got all 64 bits. I forgot to take row. Let's do it now because I put in a very interesting word in today's row taking activity. So I'm going to shift the time just so that you guys have enough time to do it. But I'm going to have to do it because I chose a word for today's row activity that I thought was funny, that no one would thought about for today's row taking activity. Alright, so the time is what? 35. I'll give you guys all the way till the end of the class to fill it in. So yeah, I set it up and then my watch went off. But then I probably was too excited about talking about floating point numbers and how we derive the bits, then I forgot. I ignored my alarm. There we go. Alright, so let me show you the answer first before I release it. Crap. Okay, I forgot to save the question. This is one really annoying feature, not feature, but one annoying point of Canvas is once you create a question, if you don't click update question, and you go all the way to save, it doesn't save it. I have made this mistake multiple times, unfortunately. Okay, so we're going to do this here. What is the row taking word for today? Fine, we're going to have to retype the whole thing. The answer is Tom Cruise. And then you guys would go like, what does Tom Cruise have anything to do with what we are doing today? I'll explain that later. And that basically will show you how my brain works in very, very strange ways. To some people, to me, it's all logical. There we go. No, it's not because of that. It's because Tom Cruise does not need a double. He does not need a double. He doesn't need a stunt person. Yeah, I remember I usually don't follow tabloid stuff except for the really funny stuff. So Matt Damon was talking to Tom Cruise once, and they were talking about doing stunts, right? Because Matt Damon has the Bourne Identity, all the Bourne Jason Bourne movies, and then Tom Cruise has all the um, Mission Impossible movies and a few more. So Matt Damon said they were talking about getting stunt people and then the safety person and all that stuff. And at one point, the conversation was about how Tom Cruise was doing all the really dangerous stunts, and Matt Damon did some of it, right? But not all of it. And because some were a little too dangerous, and then the safety person or the person who's in charge of safety said, nope, you're not going to do this. We're going to hire a stunt person to do this. And then Tom Cruise said, I don't have that problem. I just fire the person who's in charge of safety and hire another person until I get the person who say, yes, Tom, you can go ahead and do it. So he doesn't need a stunt person. Hanging out, right outside of an airplane? Sure, not a problem. There we go. It's Tom Cruise. Alrighty. I'm just going to show that one more time because some people have not been following the conversation. So the answer is Tom Cruise. Yes. It's not because I'm a big fan of Tom Cruise. It has to do with he doesn't need a double. He doesn't need a stunt person. All right. Now that that is out of the way, right? So we're gonna go back to the boring stuff. I suppose you can say that as Tom Cruise doesn't need a stunt person, I don't need a textbook. Kind of the same thing. I don't know. I think Jackie Chan probably had more bones in his body broken than Tom Cruise at this point. But Tom Cruise is catching up. Yep. All right. So, let's see. How much time do we have? Well, we got 10 minutes. Okay, that's plenty of time. So the next question is, well, tech, you can claim this all day long, but how do you know this is actually true, right? Because I can make tons of mistakes and or have no understanding of double precision floating point numbers and just kind of spill all this stuff here that seems to be coherent. So how do we check it? Okay, that's the whole thing. How do you check it? You can probably go to the internet and find out some way to do it, but I'm going to show you how I'm going to check this. Okay. The first thing I need to do is to look at all the bits, as one single value because that's what I need to do to punch in the values. So what we have here, okay, so I'm gonna use backtick in this case. So we got one bit that is the sign bit, right? And then for the exponent, we have this sequence of bits over here, which is 1 0 0 0 0 0 0 0 0 and oh, okay, I'm not typing correctly. I'll do it one more time. 1 0 0 0 0 0 0 0 0 1 1. That's for the exponent. And then we got the fractional Mantissa bits, which are from bit 51 down to bit 45, because the rest are all zeros. So we got that portion as 1 0 0 1 1 0 1, and just a bunch of zeros thereafter. Okay, so are we good so far? In terms of how I ended up with this bit pattern here. So the dot 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 is really just filling up so that we end up with 64 bits in the end. Are we good so far? Does everybody understand how I ended up with all of these bits in these specific bit positions. Excellent. Okay, so we are all there. So now I'm going to rewrite. Oh, what just happened? Oh, I have to go back to turn off dark mode. All right, so all right. So what we do now is we're going to change the way we divide the bits. Okay, so we're going to say 4 bits in the group, 4 bits in the group. Oh, wait, 4 bits in the group, 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 and so on. So the reason why I'm changing it to this particular way to break up the bits is because I want to use hexadecimal digits. Okay, so we haven't really gotten too much into hexadecimal digits, but I can just say that 1100 is A in hexadecimal, and then 0 is just 0, 0011 is 3, 1001 is 9, and the rest are all zeros. Now, because one hexadecimal digit corresponds to 4 bits, and we need 64 bits, right? So we need 16 hexadecimal digits, and now we have only 4, so I need 12 zeros after this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. And in C and C++, you can indeed specify, hexadecimal digits or base 16 numbers. And the way to do that is to use 0x as a prefix. So now we say the 64 bits, okay, representing negative 25.625. Yes, I actually remember the value is 0x, which means in hexadecimal, A039, and the rest are all zeros. And then you guys look at this and go like, how is that going to help us? Well, I'll show you. So I am going to use the rest of today's class to explain how we are going to verify this bit pattern does indeed, if you look at the bits, okay, if you chop it up into 3 parts as a 64-bit double precision floating point number according to IEEE, it will be representing the value of negative 25.625. So the way we do it is to use a very small, tiny little program that is useful. And trust me, I'm only going to use concepts that you have learned in CISP360. Or at least I thought you should have learned in CISP360. Because what I thought you should have learned does not always mean it is taught. So we'll take that into consideration. Alright, so I'm gonna type in a program, and there's no specific name for this, it's just TMP itself. Pound include stdint.h, standard integer.h. What about the 001010 part? Did I miss something? Probably. I did. Oh, okay, that's an A. Okay, so let me switch back to the browser. So, Gannon is correct. I forgot about this portion, and that is letter A in hexadecimal, which is, oh, I forgot. Oh, I made a mistake earlier too, because 1100 is supposed to be a C, not an A. So 1100 is a letter C in hexadecimal. So I'll teach you guys about base conversion from base 2 to base 16 in the next class, but I will just tell you that it's easy. Okay, it's very easy. It's a table lookup kind of thing. But I did make 2 mistakes, not just one, in the conversion by hand. All right, so getting back to the program. All right, so here's main, and in main we have a uin64_t, which is basically forcing the compiler to give me a 64-bit unsigned integer. Because if you just say unsigned, it depends on the compiler and also depends on the system. Sometimes it will give you a 32-bit number, sometimes it might even give you a 16-bit number. But this way, I'm quite sure that x is a 64-bit unsigned number. X equal to 0 because otherwise, the variable is going to be optimized out of the program. And this is the entire program, which has no double, nothing, right? So you might be asking, how is this program going to help us? This doesn't seem to do anything at all. Alright, so we're going to do a GCC to compile the program. So GCC-G to include debug information, and then -O to specify what output, what is the executable corresponding to temp.c. Okay, compile just fine. GDB into the debugger. Alright, so now we're in the debugger, and I just want to put a breakpoint on line 7. So B7 is how we set a breakpoint, and then we just run the program. Okay, and then we say, oh, tell me what is x. X has a value of 0. You guys go like, boo! What does this have anything to do with our program? So now we can say x equals to the hexadecimal number that we have specified earlier. So Control C, copy, and then over here. Oh yes, I have to use set var equals to, set var x equals to. This is the command that you have to use in GDB in order to change the value of a variable in your program. Okay, press the enter key. Alright, so now we say, oh, is it gonna work? No, it's not gonna work. This is because the way it's printed is based on the type of x, right? And x does not have a type of double. X is an unsigned 64-bit integer. So if you look at these 64 bits, okay, as a unsigned 64-bit integer, you would end up with the value in the debugger, okay? But that's not what we want, right? So some people may say, oh, I know, typecasting, right? This will do it. It's not going to do it because the double is casting the value of x, which means we are already looking at this value here, except we are typecasting this value into a double representation. So that's not going to work either. So I'll give you the solution because we are running out of time. We got 20 seconds. So here it is. There we go. This is going to get a trick done. I got 10 seconds to explain this. So we are taking the address of x, and then we say, don't look at this address as the address of a 64-bit integer. Instead, look at it as the address of a double, and then dereference it. Done. Okay, all right, fine. We have 3 seconds. We have 3 seconds. I took 3 seconds more than what I thought I would need. So there you go. Yeah, I mean, taking the address of operator really should be introduced in CISP360, typecasting 360, dereference 360. So there we go. So now we know that tag is not lying about the bits, right? Well, I don't intentionally lie, but I do make mistakes, like along the way. So this is a good verification that I did not, well, I made mistakes, but you guys helped me catch some of those mistakes, and I caught some of the other ones. So in the end, it all kind of worked out. All right, so this is all getting recorded. Okay, so if you guys have any point that you want to kind of go back in time and go like, okay, I'm not really quite sure about that, you can now go back in the video and kind of watch only specific parts of it. Again, on Thursday, we are not going to have any lecture because it's going to be our exam 1. I probably will not have a lab on Thursday, just so that we have the exam, and I cannot talk about the solution right after the exam because some people might have DSPS arrangement to take longer, so I can't really talk about the solution on Thursday. So when you're done, you can just you're done for the exam, you're done for the day. So that's kind of cool on Thursday. So no need to ask me whether there's lab on Thursday or not, but we do have lab today. Alright, so we have some questions. Is there any specific set of concepts we should be studying, or just everything up to and including signed versus unsigned? Yes. So the scope of the exam is up to binary comparison. So the L flag, the overflow, the sign flag. I mean, obviously, when we talk about the sign flag, that kind of implies that signed representation, signed integer representation, is also a part of the scope of exam 1. So that's kind of the scope of the class. you really just want to understand the concepts. Okay, do not over practice with the practice exam, because when people over practice and your exam turns out to be not using that format, those people panic because they over prepared. They basically they just keep doing whatever is in the practice exam, and they forgot about all of the other things that can also be in your exam one. So do not over practice. Yes. So I need to talk about the access code of tonight's lab. It's kind of a continuation of what we did on last Thursday, which is kind of mostly just math stuff. Um, I would say you should understand the concepts, but I don't think you want to assume that your test is going to be in the same format as the practice exam. So I would just kind of go over the entire scope of what can be in the exam and make sure that you understand all of those concepts. Uh, I think the technique to go over, to answer those questions, for question number two, question number whatever question that we went over, it's going to be the same kind of technique. So I am not going to go through some of that stuff. Yes, it is. It does start at 5:30, ends at 6:50 p.m. on Thursday. There you go. So the access code to tonight's lab is EXP. Yep, yep. With Jonathan, just kind of remind him to go over everything that is in scope and not to make any assumption that your exam is going to have the same format as the practice exam. I cannot overemphasize that. Alright, so save and publish. You should be able to get into the lab now. There you go. So I just want to confirm that because, I can do this. I can do a student view. There we go. Take the exam, take the quiz. Access code is EXP for exponent. And here we got the questions. The first four and the second four, those are basically same kind of questions. So there are only four types of questions here. 1 and 5 have the same type, 2 and 6 have the same type, and so on. Alright, so if there are no further questions, I'm gonna kind of scoot off and get something to eat, and then I'll be back in about 10 minutes. Alright, doesn't sound like people have any questions. Alright, so I'm gonna get out of screen share and streaming.